Hi folks, welcome to our video for this week. We are talking about forces still, but this time we're going to go a little bit different and we're going to start talking about forces on an inclined plane. Okay, so this is going to bring us back to that idea of vectors. Okay, the first thing I want to talk about is looking at that review section at the very start. Most of this is already posted for you, but I just want to talk about question 3 of that free body diagram where we have the inclined plane and we have this block that's going to slide down this inclined plane. And we want to be able to write out what are all of our forces associated with this situation. Okay. The first one that we're going to deal with is our force of gravity. Okay, that force of gravity is going to pull straight down, right? Although we are on this inclined plane, if we had this block, it would slide this way down there. The reason why it's going to slide down is because gravity is pulling it directly down. Okay, and then we've got our normal force, and usually we would say that our normal force is equal to our force of gravity. However, we have to remember normal force is the force of the surface, and it's perpendicular to the surface. So we have our surface going this way. So that means my normal force is going out in this direction here, and it will not equal the same as our force of gravity. Okay, and we're going to get into that when we start decomposing these vectors as well. And then if our overall motion for this block is to slide down this way, we have to remember that force of friction opposes that motion. And so we're going to have our force of friction going back this way. All right, so we are dealing with a slightly different free body diagram compared to what we've dealt with in the past, and that's why it's so important to make sure we understand how to properly do our free body diagrams, and we want to make sure that we're including them in all of our work, because it really helps us to understand the direction and eventually the magnitude of these different forces. All right, you'll also notice on the second page of the notes for this week, I've blocked out 2 of these images from that review section. Now, I'm going to go over the top one today in a moment here after I get through a few other questions or from page 3. And then the second one that's on there, we have done this one before. Or something similar to it last week, so you can try it out. I will go over it in next week's video as a review to get us back into that tension as part of next week's notes as well. Okay, so like I said, I'll come back to the boy pulling his toboggan in a moment. So let's move on to page 3. We are talking about forces in 2D. Okay, 2 dimensions. Right, we've mostly been dealing with our 1 dimension so far, either looking at the vertical portion or the horizontal portion. Now we're going to start to combine these 2. Okay, and so as we start here, as with any vectors, forces must be resolved and considered to both their magnitude and direction. Okay, so we're considering both the magnitude and the direction of these forces. Okay, so we need to really make sure we understand this. Okay, so we are going back to that vector decomposition and vector recomposition for this next little while. Okay, I do have one example here where we have 3 vectors, but most of the time that we're just going to deal with, we're just going to do the 2 vectors, or taking a vector and breaking it down into its x and its y components. Okay, so let's take a look at the first example here. We've got 2 students are pushing a crate across a frictionless surface. Okay, so let's draw our crate here. Okay, and we're on this frictionless surface. And so what do we have? We have student A pushing to the east with 75 newtons. Okay, and we've got student B pushing south with 48 newtons. Okay. Now, we can understand just by looking at this, it's going to go in an angle like this, right? It's being pushed to the east with more force than down, so it's not going to come perfectly at a 45-degree angle, but it is going to move down in this way in some sort of a southeast direction. But we want to know exactly what that's going to look like. So when we want to recombine these, we are going to make this look like we have our vector 1 here of our, so let's call this force 1. Okay. And then we are going to take our force 2 here, and we're going to add that to the end, and this is our F2. And so what we get out of here is we have this F total. Okay, so it's going to be some combination of these, and we're going to have this angle theta inside here that we need to solve for. Makes it kind of hard to see. Let's show you. There we go, that theta inside. Okay, now the beauty of this particular problem is we were talking directly east and then directly south, which gives us this right triangle situation here. Okay, so what we got here is we've got a situation of we're looking at Pythagoras. Okay, we've got our A, our B, and we're looking for C. So we're using that A squared plus B squared equals C squared situation. Okay, where our C is our hypotenuse, and in this case that is our total force that we're looking for. So if I want to rearrange this, I'm going to say that my total force is equal to that F1 squared plus F2 squared. Now this was originally square rooted. The way we get rid of the square root here is by square rooting both sides. Right, just a little bit of Pythagoras action going on here. So if we want to figure out this magnitude, we're going to take our force 1, our 75 newtons squared, plus our 48 newtons squared, and then we're just going to square root that. When we do this, we end up with a magnitude of 89 newtons. Okay? So hopefully this is the easier portion of what we're talking about here for this one. Okay? When it comes to this angle over here, again, we've got the right triangle, so we can just use our trig identities. And based on this angle, we have our opposite and our adjacent. So we are looking then, change colors here real quick for you. The tan of theta equals our opposite over our adjacent, right? Our F2 over our F1, or we could say that the theta equals the inverse tan of that 48 divided by 75, and this gives me an angle of 33 degrees. Now, the direction we put here, now I found 33 degrees, and that's going to the east. We're going south of the east direction. So let's put that in there. Let's say that is south of east. Okay. So hopefully we remember this from before spring break. I realized that was a couple months ago, but hopefully we kind of remember this. But really, we're just building on our Math 10 skills, understanding that we are dealing with these right angles, where we can decompose these into our x and our y components, as we'll see in a moment, or we can recombine these when we have a south and a east situation, or really any of those north, south, east, or west directions. Okay, that'll be about as far as we have to go. We're going to deal with these right triangles. Okay, so there's no need to use our sine law or our cosine law. If you know them, you know how to use them, you can set it up properly, by all means. I'm going to continue with this decomposition, recomposition model that we've dealt with in the past. Okay. Now, if there are more than two vectors that we're trying to add, we're going to use the component method. Okay, so we're using this component method where we're going to take each of these vectors and we're going to decompose them into their x and y components. Then we can add up all the x values, add up all the y values, and then we're back into a similar situation like we dealt with in that previous problem. Okay. Now, for our first example here, we want to add 3 different vectors. Okay, but we can decompose these all into our x and y situations. All right. Force 1. We have 35 newtons at 20 degrees. Okay? And we're going to use this to find this F1x and this F1y. Okay. And so if we're looking at this whole triangle here, if we're looking at this x portion, well, that is the adjacent side to our angle, and we have the hypotenuse. So that means that this FIX, actually, let's go over here. We're going to say that the cosine, right, I said adjacent over hypotenuse. So cosine of theta equals our F1x over our F1 total, right? Or we rearrange that and say that our F1x is equal to F1 times the cosine of theta. So for this particular problem here, I'm going to take my 35 newtons times the cosine of 20, and I'm going to get 32.89 newtons. Okay, remember, 2 sig figs in our problem. We're going to carry a couple extra sig figs to do our calculations, and then we'll round it back at the end. Okay, now similar to our fx being the cosine, we can also look at our F1y. Okay, that is the opposite and our hypotenuse, so we're looking at the sine of theta equals that F1y over the F1 total, or F1y equals F1 times the sine of theta. So, and again, when I go to plug this in, I'm going to take my 35 newtons times by the sine of 20 degrees and get a value of 11.97 newtons. Once again, carrying those extra sig figs through this problem. Okay. So we have these 2 values here. Let's move on to our number 2, F2. We are downwards in this direction here. We have 45 newtons at an angle of 50 degrees. Okay. Once again, we want to break this down. We need to find our F2y and our F2x. Okay. If we are looking at our F2x, okay, once again, F2x is going to equal our F2 total times the cosine of theta. We're also going to look at that F2y is the F2, or the F net that we have here, multiplied by the sine of theta. Okay, so looking at our x component, we're going to take our 45 newtons times by the cosine of 50 degrees, and this gives me a value of 28.93 newtons. And if I take my 45 newtons times the sine of 50, that gives me down here a 34.47 as my F2y, and once again, newtons. Okay? So we're just taking our component, or our total vector that we have here, and using the angle provided and our understanding of trig identities to get our F2x and our F2y. our last force that we have here, our F3, we just have this horizontal line of 65 newtons. Okay. We still need to break this down. However, when we look at our F3y, there is no vertical component. This is 0 newtons, and we have strictly this horizontal going into the positive direction, and so we have 65 newtons. Okay? So hopefully that helps breaking down this. Now, the second part of this is we want to take all three of these vectors that we had, these F1, 2, and 3, and we want to recombine them. So we want to know what is the F net for F1 plus F2 plus F3. Okay? And the order that we have these doesn't matter. Okay, I want to be really clear on that. I want to make sure that we understand that the order that we add things doesn't matter. 1 plus 2 plus 3 is the same as 1 plus 3 plus 2, right? That's not going to matter. Both of those are going to equal to 6. So I'm going to use that to kind of help us rearrange these. And so we have our F1 here. We have our F3 going straight across, and then we have our F2 going down like this, and we want to know our F net or our F resultant, whatever it is that you would like to call that, right? So we can say that's F net or F resultant, right? So rather looking at the net force or the resultant force by adding all of these up. All right. So, actually, I'm going to leave that on there in a smaller version. That's F1, F3, F2. Okay. Now, we're going to look at our total F net in the X direction. Okay. So, looking back at the previous examples that we just did, we had our F1, as we see here, going to the right, so that gives us a positive value, and we had 32.89 newtons. Our F3 was only in the horizontal, only going that positive direction, and that was those 65 newtons for the X direction. And then looking at our F2, that last piece, we also had a value going to the right, so also positive 28.93 newtons. This gives us a total X value of 126.82 newtons. Okay, now we're going to do something very similar for our Y. We're going to look at the F net Y component. Okay, looking at this first vector F1, we are in the upwards direction, so we're going to call that positive. So for F1, our Y component was 11.97. Our F3 component we said was completely horizontal and therefore no vertical, so we are looking at 0 for the F3 component. Now, when we're looking at F2, this is going downwards, so a negative value, right? So we are going to add to that the negative 34.47 newtons, right? It's going, we said positive is, or sorry, upwards is positive, so downwards would be negative, so we're ending with a negative value for that portion there. And this gives us a grand total of negative 22.5 newtons for our F net Y. Okay. And when we drew in that resultant, the negative value kind of makes sense. It seems like it's going a little bit down. All right. Now, let's redraw this in the situation that we're looking for. Our resultant, we had our F net X was equal to 126.82 newtons. We had our F net y going downwards, it was that negative value, okay, of 22.5 newtons. And we are looking over here at our F net or our F total or whatever it is that you want to call it, right? So when we recompose these, now that we have our Fx and our Fy, this is just like the first example, we're just going to recombine these. So when we want to look at this F net, it's going to equal the square root of the Fx squared plus the Fy squared. And this gives me a grand total of 129 newtons, which I guess since we only had 2 sig figs in any of the values given to us beforehand, let's just rearrange that and say it's 130 newtons. Okay, that's the magnitude. Now we need to find our direction. And remember, tan of theta, we're looking at this theta inside here, is our opposite over our adjacent, so that equals our Fy divided by our Fx, or that the theta is the inverse tan of the Fy over the Fx. And this gives me a value of 10 degrees. But we also want to have a direction. That 10 doesn't really help us. There can be lots of different spots. So if we are looking at the way we've drawn this, we could say that is down, or 10 degrees down of right, or more common, we would do this north, south, east, west, and so we are 10 degrees south of east. Okay, so our overall net vector here is going to be 130 newtons at 10 degrees south of east. Okay, so hopefully that helps with our reminder of decomposing our vectors and recomposing them. Okay, now let's take a look back at that the boy pulling his toboggan example from the previous page. All right, we're going back to the previous page where we're talking a little bit of review, but I guess kind of a combination. Review and new stuff here. So this boy is pulling his 8-kilogram toboggan by a rope that angles 32 degrees above the horizontal. If his 36-kilogram sister sits in the toboggan, how much force does he need to exert to accelerate them at 2.25 meters per second squared? There is no discussion of friction in here, so we will assume that coefficient of friction is 0, or that there is no friction in this situation. So we want to take a look here. Here is our toboggan. We need our free body diagram. Well, this is on a horizontal surface, so we have force of gravity going down. We have our normal force pointing up. Okay. Our applied force is up here at that angle of 32 degrees. Okay. And since our motion, we want to accelerate this way. Change color. We want to accelerate at 2.25 meters per second squared, and we are looking strictly at the horizontal portion here. So if we wanted to decompose this applied force, because since we are on horizontal, the gravity and normal are the same. Okay, we're going to get into ones where they're not the same soon. For this one here, we're looking at, we want to know what this F applied needs to be when we have Fx here, Fy here, and we have that 32 degrees. Okay, well, we want to have this portion here. So if we want to look at this Fx, well, f of x, we're looking at mass times acceleration. In this case, our mass is the 8-kilogram toboggan plus the 36-kilogram sister. And then we're going to multiply that by the acceleration of 2.25 meters per second squared. So essentially 44 times 2.25 gives us 99.0 newtons. Right? So this is our x component here. We need to find what the applied force is going to be. Okay? So again, x is adjacent. Applied is the hypotenuse. So we are looking at the cosine of theta is equal to the adjacent, our fx, divided by f applied. Okay? We are looking for this f applied. What is the total force need to be applied by the boy? So we're just going to do this as then our fx divided by the cosine of theta. So our 99 newtons divided by the cosine of 32 gives me a value of 120 newtons required to accelerate the toboggan and the sister at 2.25 meters per second squared if the boy is pulling upwards at 32 degrees. Okay. Hopefully that one makes sense. We're just decomposing their vector into what is required to move in a horizontal motion and converting that into an angled force. Okay. Hopefully that helps. Let's move on to discussing inclined planes. All right. We're now talking about these inclined planes. We've kindly mentioned this in a little bit of our review and just looking at a few different images and things like that. But what we want to understand here is that if a ball is sitting on a flat surface, horizontal flat surface, it's not going to move. Not without a force, right? So we've got this f of g pointing down, and in this case, our Fn points directly upwards. Okay, and this gives us an F net equal to 0. If it wasn't moving beforehand, it's not going to move now. Okay, now where this differs though is when we're looking at this inclined plane situation, our force of gravity is pulling it straight down, and then we end up with this F net in this direction here. We do have an F net. So that must mean that our normal force is not equal to the force of gravity. Okay, so let's recombine this into an overall inclined plane and see a little bit what's going on. So when we're looking here, what we have is we've got our force of gravity pulling this ball straight down. Okay, gravity always pulls straight down. Our normal force, though, is always Fn, not always straight up. Okay? Fn is always perpendicular to the surface. Okay, and remember we use this symbol here for perpendicular where it's forming a right angle with that surface. So if our surface is this way, that means our Fn is somewhere out that way. Okay, so Fn is always perpendicular to straight up. It is not, it's always perpendicular to surface. It is not always straight up. Okay, and so if we're looking at this, what we have is we have force of gravity going down here. We would have our normal force going out this way, and our F net in this direction. And we are forming our right triangle right here, okay, between the F net and the F normal, okay? And so for these situations, whenever we're on an inclined plane, we want to realize that the force of gravity is greater than the normal force. Okay, this will have a very big impact on how we solve these problems. Okay. Now, I'm using the ball for an example because we can understand how a ball would roll down these. But when we're dealing with our free body diagrams, we are usually dealing with boxes. Okay. So we have this angle. This marker's running out. Let's just stick with the black. We have our angle theta in here. And we have our box over here. So how does this look? Well, force of gravity is pulling it straight down. Our normal force is going perpendicular to this surface. So we have two pieces what's going on here. We have this force of gravity is being broken down into two components. Okay. The first component is coming this way down the ramp. We're going to call this FG parallel to the surface. Okay. Also on here, we have this portion coming down here, and this is our FG perpendicular. Okay, so in this situation, our FG perpendicular is equal to our Fn, our normal force. Okay, and based on our properties of triangles, this angle theta that we have here on our ramp is the angle theta inside here. So this piece inside here looks something. We have our F theta. This is our overall, I'll use the colors I've mentioned here. So this is our overall force of gravity. This over here is our FG parallel. And this bottom piece is our FG perpendicular. Okay? So I really wanted to kind of break it down for this, and I'm going to use these parallel and perpendicular quite a bit, but we're going to notice something. When we're talking about FG parallel, or sorry, FG perpendicular, this will equal our force of gravity cosine theta. Our FG parallel will equal the FG sine of theta. Okay? Based on all the problems I'm going to give you for the rest of this course, we will always be this way. Put that into your toolbox. Make sure you have that on your formula sheet. Whatever it is that you use, always have those two down there. And then remember, our force of gravity perpendicular is equal to the force of normal force. Okay, so when we start talking about friction, we need to use this portion to help us figure out that force of friction. Okay, and I'll get to that in our examples here shortly. Okay. We got two statements here, two important things that we want to notice from this. One, only the parallel component of the force of gravity pulls down the ramp. Okay, so that force of gravity parallel allows us to figure out the force that's going to be pulling us down the ramp and allows us to figure out the acceleration. Okay. For part two, the perpendicular part, perpendicular portion, Okay, so only the perpendicular component is equal and opposite to Fn, or our normal force. Okay, so hopefully that helps us understand how we break down these inclined plane problems and how we can move forward to start solving them. Let's take a look at a couple of examples to figure out how this works. All right, first example. We have our 8 kilogram block sliding down a frictionless inclined plane as shown. What is the acceleration on the 8 kilogram mass if our angle is 35 degrees? Well, what do we got here? What's going on? Force of gravity is coming down this way. FG parallel is this direction. And our Fn is upwards, and it is equal and opposite to the FG perpendicular. Okay. Now, when it comes to this type of problem, what is our F net? Well, our F net is equal to our mass times acceleration. Okay, and our net force is the only force that's coming down this way, and so that's going to equal to that FG parallel. Okay. And so when we look at this, we're going to say then, we said that FG parallel is equal to FG. So let's just, FG parallel is equal to the FG sine of theta. Okay, and our FG is m times g times the sine of theta. So we plug in our 8 kilograms times our 9.81 times the sine of 35, and we get 44.97 newtons. Now that's our FG parallel, so that means that it is also equal to our mass times acceleration. So our acceleration is then our FG parallel divided by the mass, or 44.97 divided by our 8 kilograms, and we end up with 5.6 meters per second squared. Okay. So when we're looking at this, our F net is the parallel component, the part that's going down the ramp. Okay, and when we draw that out, we realize that that is our FG sine theta. Okay, now I'm going to go back a step here. And I had said that the FG parallel is our net, which is our mass times acceleration. Well, if I plug that in as my mass times acceleration, I can divide out both of those and realize that my acceleration in this portion is our g sine theta. So when all we're doing is looking for acceleration, the mass doesn't matter. Okay? Just like gravity everywhere on Earth is 9.81, the acceleration for any of these things on inclined planes is always going to be g sine theta. So if all we're asking for is the acceleration, you can plug it in this way. Okay? Hopefully that helps make a little shortcut for you to make things a little bit easier. Let's move on to the second example. All right, example number 2. How much force is required to push an 11 kilogram block up a frictionless ramp, as shown, with a constant velocity? Okay, so what do we want to know here? So let's think about this. We have acceleration equal to 0, so therefore F net also equals 0. All right. So if this is going up, so that means this is our F applied. We have our force of gravity pulling down. Okay. We have our normal force perpendicular to the ramp. Okay. And we had said that the force of gravity that's pulling it downwards in this direction is our FG parallel, and then our FG perpendicular is the opposite direction of this FN normal. So I want to push it up the ramp at constant velocity. Well, Fn we know is the same as our FG perpendicular, so really all we're doing is looking at, I can draw that in there in orange for you if you'd like, FG perpendicular. So we're looking at our FG parallel and our F applied. Okay, F net is going to equal our F applied minus our force of gravity parallel. And we've said that all of this equals 0. So then our F applied must equal our FG parallel. And from previous notes, previous examples, we know that the FG parallel is FG sine of theta. Okay? So we want to know about the force required to push this up. So we are looking at the full here. So this is now mg sine theta. So we go to plug this in. We have our mass is our 11 kilograms. Our gravity is 9.81 and our theta is 58 degrees. This gives us an applied force of 91 newtons to have a constant velocity pushing this block up a frictionless ramp. Okay. In this problem, because we want the force, the mass does matter and it does count. We do need to include it. Okay. So that's our first two examples. One going down the slope, a frictionless surface. Second one is going up that frictionless surface. Let's take a look at what happens to a block sliding down a ramp with some friction. All right, our final example here that we're going to deal with is a 15 kilogram block sits on an inclined ramp with coefficient of friction of 0.21. We want to know what is the overall acceleration of this block. All right. Let's start by drawing out all of our different forces that we have here. We have force of gravity coming straight down. Associated with that, going this way, we have our force of gravity parallel, right? Parallel to the surface we're traveling on. And we have this piece here, which I'll write in orange. This is our FG perpendicular. Okay. We always want to include, we have perpendicular to the surface here. This is our normal force. Okay. And then because we have friction, friction's opposing motion. This block should be sliding downwards. So in that case, our force of friction is opposing that motion. Friction always opposes the motion. So for this block to be free flying and sliding down, our force of friction is pointing upwards. So this does give us a bit more complex of a free body diagram. Please make sure you include those in all of these problems. It helps you to understand what's going on, helps you to visualize what's going on, and helps you to also realize that this angle theta here is also this theta inside that bottom corner of here. Okay. Now, we want to make a couple pieces off to the side here. Force of gravity perpendicular is the gravity portion that pulls in here, and so this Fn is also equal to that Fg perpendicular. Okay. Now, force of friction was mu Fn when we were on a horizontal surface, our force of friction is still that mu Fn in these situations. Okay? So we need to make sure that we're clear on that. And then because it's equal and opposite to that perpendicular, we can say the force of friction is then mu times the Fg perpendicular. I also said that this Fg perpendicular is our force of gravity times the cosine of the angle we are provided. Okay? So it's very important to make sure we're paying attention to how these all work together. Okay? Now, if we are looking at this force of friction, we have our mu Fg cosine theta. So we have our 0.21 times our mass of 15, our coefficient 0.21 times our mass of 15 times gravity 9.81 times the cosine of 40, right? Because mu mg cosine theta, this gives me a force of friction equal to 23.65 newtons. Okay. And when we look at, we want to know our F net, right? We want to find the overall acceleration. So we want to figure out what our F net is, mass times acceleration, right? We're looking for this overall acceleration. Well, this block is going to be accelerating down this ramp. So that means that our Fg net must be, our F net must be the Fg parallel minus the force of friction, and that is equal to our overall mass times our overall acceleration, or we can say acceleration is the force of gravity parallel minus the force of friction divided by the overall mass. We've already calculated our force of friction. We were provided with their mass, so we need to find this Fg parallel. Well, Fg parallel is equal to our Fg sine theta. So Fg sine theta is mg times the sine of theta, and I get a value of 94.49 newtons. So when I'm down here to try to find my acceleration, I have my 94.49 newtons as my force of gravity parallel, pulling it down the ramp. I have my 23.65 newtons as my force of friction, slowing it down as it tries to go down the ramp. And then I divide by my mass of 15. This gives me an overall acceleration of 4.7 meters per second squared. Sorry for my units not looking that great. Okay. So hopefully, now this is a very complex problem based on where we're at right now. Hopefully this all makes sense. Now, I said in that first example that when we're looking for acceleration, mass is not a factor. So I want to get rid of this stuff for a second now that we've seen what's going on. And I want to go back to this acceleration equals the Fg parallel minus the force of friction divided by mass. Well, Fg parallel, we could say, is our force of gravity times the sine of theta, or our mg sine theta. Our force of friction, we said, was mu mg cosine of that angle. And all of this is divided by mass. That mass can be canceled out, and it will simplify that a little bit, although it's not all that necessary for you to do it. We went through and figured out how that would work without it. Okay, feel free to double check how that works with if we ignore the mass in here, right? Because we've looked at the F net is the Fg prime, or Fg parallel times the minus the FF. And so when we divide out that mass, we end up with this formula here, and that is our acceleration. Okay. So when we're looking at the acceleration, mass is not important. However, to solve our problems, it might be better to keep those in until we're better at handling these. Okay. Lots of questions posted on online there for you. Please, if you have any questions while you're working through this, post those in our teams, and I will get back to you as soon as possible. And we will have office hours later this week, as I've already posted on Schoology. Take care, everyone. Be safe. Stay healthy.